Right, so here we go with A2 Physics from CCEA, and this is Fields and Their Applications from June 2016. Let's get started. Question 1, we have a planet here of mass little m, and it's in a circular orbit of radius d around this planet of mass big M, and it says that the period time for this orbit is big T. So in this first part we're asked to state Newton's law of universal gravitation in words. Well, let's establish what it looks like in symbols first. So you've got G, M1, M2 over R squared. So that means that we have a force that's proportional to the product of the masses and a force that's inversely proportional to the square of their separation. So you want to just think about those two concepts and then put them into words. So F is proportional to M1 times M2, and F is proportional to 1 over R squared. That's really what you want to do, and then write that in words. Now for demonstrating Kepler's law, we always put the gravitational force equal to the circular motion force, and then we just start rearranging that to get the t squared and d cubed thing that we're interested in. So remember that omega is 2 pi over t, so omega squared is 4 pi squared over t squared, and then you basically sub that in for omega and rearrange, and you should eventually start to get your t squared on one side, put all your d values to the other to get the d cubed thing that we're interested in, and then simplify all that. So we put all our d terms to this side with only our t squared on the other side, and then the job is to simplify that to get all the d terms together. And you can see we've got a d squared and a d, so they'll become a d cubed, and then we just simplify what we've got left. There's two little m's there that are going to cancel, leaving only the big M, and you should see quite quickly that we're going to get this 4 pi squared over gm that they've asked for. So you always just start with putting gravitation equal to the centripetal force, because it's gravity that's providing it, and we can put those equal, and then you're just simplifying. So practice this and you should be okay with it. So at this point we've got the constant of proportionality that they asked us to find, and that's what we were trying to do. So we're given these values for Saturn and Rhea, and we can use the equation that we've just looked at to look at the period of Rhea, just putting in the 4 pi squared over gm that we got in the previous part, and the d cubed thing, and just substituting into that. So we get 4 pi squared times the d cubed and over the g times the big M for Saturn, and just substituting values in there, and then the idea would be to put that through your calculator and see what period you get for Rhea. So if we feed that into your calculator, we get a value of 390,533, and that's going to be in seconds because these are all SI units. So we're going to need to divide that by the number of seconds in a day in order to get it converted into days, so 60 times 60 times 24. So if we divide by that, we will get the value in days, which turns out to be 4.52. Okay. Right, determine the gravitational field strength on the surface of Rhea. So we've got an equation for that little g is gm over r squared, where we're talking a radius of the planet out from the centre. So big G, mass of Rhea, and then the radius of Rhea to get us how far we are out from the centre. .64 times 10 to the 5, and that's because it needs to be in meters. Okay, so gm over r squared, feed that into the calculator, and we get this value of 0.26 newtons per kilogram. 2a. Determine the electric field strength in a vacuum 5 centimeters from a plus 40 microcoulomb point charge. So we've got this positive point charge here, and we're interested in the electric field 5 centimeters away from it. So we've got that E is 1 over 4 pi epsilon naught times the Q over the r squared. So there are two basic aspects to this question. One is your knowledge and ability to use your equations, and the second one is that these numbers that have to go in also need unit conversions in order to get an SI answer, and we are expected to have an SI answer of newtons per coulomb here. So we need to watch that when we fill this in, we convert these correctly. So we have this useful little value of what 1 over 4 pi epsilon naught is, of 8.99 times 10 to the 9. So we can use that quickly in our equations when we're subbing in. So we've got a Q on the top line of 40 micro, so that's times 10 to the minus 6. And we're squaring on the bottom 5 centimeters, which is 5 times 10 to the minus 2, and then we're squaring that. And so we're just taking the time to make sure that we're subbing in with correct units to that equation. So putting that through the calculator, we get a value, taking I suppose the first few significant figures of 1.44 times 10 to the 8 newtons per coulomb. So now we're told that a 60 microcoulomb negative charge is positioned 5 centimeters from the 40 microcoulomb point charge. Determine the magnitude and direction of the force on the 60 microcoulomb charge. We already have the field 5 centimeters away, so we're interested in applying that to the new charge that we've introduced. The force on that new charge is going to be the field at that location times the new charge. And so that's going to be 1.44 times 10 to the 8 multiplied by the 60 microcoulombs. And that works out to be 8640 newtons. Now as far as a direction is concerned, if we have a plus 40 here, and we have a minus 60 here, then they're going to be attracting. So the direction of this is going to be towards our only reference point. We'll know it'll be towards the 40, so that's what we have to say. So we just indicate that it will be towards the positive 40 microcoulomb charge, because that's our only reference point. This 60 could be anywhere around this, so we have no specific direction. It could be anywhere in 3 dimensions, not only in 2, but we do know that it will be pulled towards that charge.